If I drop off because of internet problems, someone else please take over. Okay.
Will do. So Maria, we'll just wait a minute for people to join.
Sounds good.
We typically start at about 1 after the hour. Thank you. Okay. All right, let's begin. Welcome everybody to this week's Green Bank Observatory Community Zoom. I'm Jim Jackson, the director here. Just a few things to report about the status of the observatory. We are coming out of our soft COVID lockdown, and so we will be reopening March 1st. So that means that we will be able to entertain visitors. And so we encourage you that if you have observing time, please do come if you can, or to work on your data, that would be great. Just there is a requirement for a COVID vaccination and booster. So in order to set up your visit, we'll have to see a vaccination card that shows you've been boosted recently. Proposals are in and they're being evaluated. Proposal pressure at Green Bank is similar to last semester. We are undergoing the technical reviews now, and the TAC will meet in a few weeks. One interesting event coming up in mid-October, October 17th, Green Bank is going to be celebrating its 65th anniversary. So we're going to have a party and a seminar, a conference, and it'll be a lot of fun. So we're going to review our multifarious and scientific discoveries, and should be a great time. So if you're interested, stay tuned for details. We're organizing that. And we're undergoing right now the remote observing training workshop for users. So it may be a little late, but you could probably still jump on if you're interested in attending. So that's all from Green Bank. I'll hand it over to Jay.
Thanks very much, Jim. I'd like to welcome everyone to the latest in our series of webinars featuring results from GBT science. And our speaker today is Maria Charisi from Vanderbilt University, and she'll be speaking to us on NanoGrav limits on supermassive black hole binaries in massive galaxies. I'd like to remind everyone to submit questions using the Q&A box to the lower right. We'll deal with those at the end of the talk, and also remind everyone that these sessions are recorded, and so they will be available through our website for future viewing within a day or two of this presentation. Take it away, Maria. We're not hearing you, we're seeing your slides.
Apologies, I was trying to find the button to unmute myself.
Okay, you're set now.
So thank you for the invitation. Yes, I'm very happy to be talking about this paper that heavily used data from the Green Bank Observatory and talk about limits on supermassive black hole binaries in massive and nearby galaxies derived from recent NanoGrav upper limits. So first of all, as we probably all know, from observations of nearby galaxy, we know that massive galaxies host supermassive black holes in their centers with mass of 10 to the 5 to 10 to the 10. And the mass of the central supermassive black hole is a very important component of the host galaxy because the mass of the black hole correlates with several properties of the host galaxy. For example, here I'm showing the very famous M-sigma relationship. So the y-axis is the mass of the supermassive black hole, and the x-axis is the velocity dispersion of the stellar bulbs. And you can see that we have a very tight correlation that spans several orders of magnitude. And this correlation and other correlations like that have been used to suggest that the central supermassive black hole and the host galaxy co-evolve somehow, even though we don't know exactly the exact mechanisms that cause this correlation. We also know that in hierarchical structure formation, galaxies are built up through frequent mergers of lower mass progenitors. So the natural outcome of a galaxy merger will be a post-merger galaxy that has two supermassive black holes. These two black holes lose energy and angular momentum as the galaxy merger progresses, and they end up at smaller and smaller separations. When they get to parsec scale, they form a Keplerian bound binary, and when they progress to even smaller separations, they become very promising sources of low frequency gravitational waves. So, of course, we are very happy that we live in this, the era of gravitational wave astronomy. We have gotten a lot of excitement in the last 5 or 6 years from LIGO with multiple binary mergers of stellar mass black holes. The black holes of the supermassive kind that I'm discussing today, they have low frequencies that cannot be detected from the ground. So the most massive of those, the ones that have mass of 10 to the 8 to 10 to the 10, they emit nanohertz gravitational wave frequencies, and they can be detected with pulsar timing arrays. The least massive of the supermassive black hole binaries, the ones that have mass 10 to the 5 to 10 to the 7, they emit millihertz gravitational waves, and they will be detectable in 10 to 15 years by LISA. So today I'm gonna focus on pulsar timing arrays and how we can produce a galactic scale detector for gravitational waves using pulsars. Pulsars are the most stable clocks on the sky. They are magnetized neutron stars that have a radiation beam along the magnetic axis, and also they're very stable rotators. So if the rotation axis is misaligned with the magnetic axis, that gives rise to this lighthouse effect that I'm showing here. So as the pulsar rotates, the radiation beam swipes our line of sight, and we can record these repeating pulses with radio telescopes like the GBT here on Earth. Because they are very stable rotators, the pulses repeat very precisely. Of course, the signal here is kind of exaggerated. The pulses are not that bright typically, and that's one of the reasons why we need access to the biggest telescopes for pulsar timing. And how exactly do we build this galactic scale detector? Here it's an animation. We have a galaxy merger that produces a supermassive black hole binary in a nearby galaxy. And as the gravitational waves pass through our own galaxy, they will squeeze and stretch the space-time. So they will squeeze and stretch the distance between the Earth and the pulsars. So some of the pulses will have to travel a longer distance, some will have to travel a shorter distance. And so instead of this very precisely repeating pattern, we will see some pulses arriving sooner, some pulses arriving later. And if we see these coherent deviations in the arrival time of many pulsars along the sky, we can detect gravitational waves. The reason we need many pulsars is because we cannot rely on one single pulsar because maybe there's something we don't understand, but if we see a correlated signal across many pulsars, we can build our confidence. And this is the reason, of course, we need many big radio telescopes. And this is an international effort. Here in the US, we have the NanoGrav Collaboration, which starts for the North American Nanohertz Observatory for gravitational waves. That relies heavily on GBT observations. We used to have Arecibo, which unfortunately we have lost. And of course, we have many international colleagues with their big radio telescopes, like the Parks in Australia, several here in Europe, and more recently formed PTAs like the Indian Pulsar Timing Array and the Chinese Pulsar Timing Array that uses FAST. We are collecting data with many radio telescopes, and we are trying to detect primarily two signals. One is the gravitational wave background from the superposition of many supermassive black hole binaries. So here I'm showing the characteristic strain, which quantifies this squeezing and stretching of space-time as a function of frequency. The gravitational wave background will give rise to a signal, a spectrum that is a power law as a function of frequency. And then on top of it, we should be able to detect individually resolvable binaries that are loud and can stand above the background. This will have, these are monochromatic gravitational waves because we detect the binaries a long time before the coalescence. And today I'm gonna focus on this type of signal. Of course, as you know, we haven't detected low frequency gravitational waves yet. And since we haven't detected, what we are doing is we are placing limits using our data. So this is a sky map that shows the gravitational wave upper limits at 8 nanohertz, which is the most sensitive frequency of NanoGrav, as a function of the sky position. And with stars are the pulsars that we are timing. And you can see that at the part of the sky that we have many pulsars, we have more informative constraints, more stringent constraints, whereas at the other half of the sky, where we don't have that many pulsars, the limits are not that informative. So what I wanted to do in this NanoGrav paper that I led was practically use a map like this and put it into astrophysical context. Because, for example, if I point a part of the sky and I tell you that the strain upper limit is something like 10 to the minus 15, that doesn't tell you much. But if I tell you that in the galaxy M87, we can exclude the presence of a binary with these parameters for this frequency range, hopefully that's more informative. So the first step for that was to build a galaxy catalog that contains all the potential hosts of supermassive black hole binaries. For this, I used the 2-mass redshift survey, which is a map, a 3-dimensional map of the galaxies in the local universe. It contains 45,000 galaxies and it's complete to 300 megaparsec. It's complete to bigger distances if we consider the most massive galaxies that we are interested when we talk about nanohertz gravitational waves. So the quantities we need to have for these galaxies, because we are thinking about gravitational waves, we need the distance of the galaxy and therefore the distance of the potential binary, because a binary that is more nearby emits a stronger gravitational wave signal. And we also need the mass of the central supermassive black hole, which we can assume is the mass of the binary. Again, the more massive the binary, the stronger the gravitational wave signal. I'm not going to go into too much detail on how we build this catalog. But in terms of distances in the local universe, it's not very trivial to convert redshift to distance because we have infall to the local clusters. So we used a few catalogs that have quality distance measurements to these galaxies. And if we didn't have a distance measurement, we corrected for this cluster infall. And for the black hole masses, we either used dynamical mass measurements, which are available for about 100 galaxies. And if not, we used the global correlations of the black hole mass with other observable properties of the galaxies, like the M sigma that I was showing in the beginning. So this is the most comprehensive catalog for multi-messenger observations, and it's publicly available with the paper. And now that we had this catalog, the next step was to find how many of these galaxies are within the volume that NanoGrav can probe. So we populate each one of these galaxies with tentative supermassive black hole binaries in the most, let's say, optimistic scenario for detection. That means equal mass binary in a circular orbit emitting at 8 nanohertz, which is the most sensitive frequency of NanoGrav. And then we compare the strain that we would get from these binaries with the upper limits. And it turns out that there are about 200 galaxies that are within our sensitivity limits. These galaxies are in the relatively nearby universe, up to 500 megaparsec. They're very special galaxies. You can see the mass of the central supermassive black hole is at least 10 to the 9. So these are the most massive galaxies in the nearby universe. And also you can see they're distributed mostly at the most sensitive part of the sky. So since we haven't detected gravitational wave jets, we can point to each galaxy and derive upper limits. So this is the next step of what I did. I used the NanoGrav 11-year dataset, and for each of these galaxies, I placed an upper limit as a function of frequency. It is important to run the upper limit analysis for each individual galaxy. Remember, I was showing the map of the upper limits, and they're very heterogeneous on the sky. Once we have the strain upper limit, that depends on the distance of the binary, the frequency, which we vary here in the analysis, and the chirp mass. So since we have the distance from the galaxy catalog, we can convert the strain upper limit to a chirp mass upper limit, again, as a function of frequency. This is the middle panel here. And the chirp mass depends on the total mass of the binary and the mass ratio. So if I assume that the total mass of the binary is equal to the mass of the central supermassive black hole, which again I have from the galaxy, then I can place a constraint on the mass ratio, which is the bottom panel I'm showing here. And you can see in this example, for example, that for this galaxy, we can place very informative constraints. If there is a secondary, if there is a binary there, the secondary black hole must be much less massive than the primary. So it has to be 10 times less massive than the primary. And this is very exciting because this is roughly the level of constraints we can place for a binary companion for Sagittarius A star. So Pulsar Timing Arrays already place constraints that are comparable to constraints we can place on a binary in the Milky Way with other methods. I will just show you some limits on different galaxies, just to convince you that we can place good constraints on more than one galaxies. Here are different galaxies, and you can see the masses and the distances of these galaxies. The top panel corresponds to some galaxies chosen at the sensitive half of the sky. The bottom panel is at the least sensitive half of the sky. One common feature is that the limits become flat at high frequencies. So for example, I can place the limits in one of the high frequency, and that can extend to higher and higher frequencies. So on the right panel, I'm showing practically the limits for the entire population as a function of the distance and the mass of the galaxy for all the galaxies. Color-coded, this is at a fixed frequency of 8 nanohertz, and the color coding is the 95% upper limit on the mass ratio. So with dark blue is the most informative constraints, and with yellow, the least informative constraints. So for example, if we look at the fixed distance, you can see that we can place better constraints if we have a more massive galaxy, and therefore a more massive tentative binary. If I look at the fixed mass, then I have better constraints for galaxies that are more nearby. Again, the top panel is for the most sensitive part of the sky. The bottom panel is for the least sensitive part of the sky. We have a similar trend in both just at the least sensitive part of the sky, we can probe fewer galaxies, and they have to be more massive and more nearby. So given these constraints, and this is almost the last slide, we wanted to ask another question. Can we tell anything about major galaxy mergers? So these are very important for galaxy evolutions, and they're galaxy mergers between galaxies that have similar mass. Again, because I was telling you that the mass of the central supermassive black hole correlates with the mass of the galaxy, we can assume that the binary, the final mass ratio that the binary will have, will reflect the initial mass ratio of the galaxies. So if we can constrain the binary mass ratio to be less than 1/4, we can assume that we can exclude a binary that was delivered by a major merger. There are a few assumptions here and a few caveats, but let's go with it. So here each bar is a different galaxy, and the bar shows the frequency where we can exclude a binary with a mass ratio of 1/4. Again, it's color coded with the distance, and you can see for the most nearby galaxies, we can exclude major binaries delivered by major galaxy mergers for a significant frequency range. Given these constraints, we also place the constraint on the density of binaries delivered by galaxy mergers, which is the black line here. To the best of our knowledge, this is the first such constraint that was delivered based on gravitational wave alones. You can see that we have huge error bars, though, that reflects the uncertainty on the mass measurements. And just very briefly, the takeaway points from this is that we are at an exciting era, that we have interesting astrophysical constraints from pulsar timing arrays that heavily rely on data from the GBT. Here I showed you that we have compiled a galaxy catalog for multi-messenger observations, which is publicly available. And then we can constrain hypothetical binaries in massive and nearby galaxies. The constraints we can place are comparable to the Milky Way. And for the first time, we could place a constraint on the number density of major mergers in the local universe. And of course, if you have questions or if you want to know more, the paper is out, and I'm happy to take questions.
Thank you very much for a most interesting presentation. Let me remind everyone to use the Q&A box in the lower right center of your screen to submit questions. I have one right away. First of all, I had not appreciated that the intensity of the effect drops off only linearly with distance. But what is the approximate distance between the black holes that you are most sensitive to? Of a binary pair.
Right. So this is here. So we are mostly right now. This is the 11-year data set from NanoGrav, and this is the last one that has been analyzed for individually resolvable binaries. We have already collected data that span 15 years. So based on this, on the 11-year data set, it's outdated by almost 4 years now. It just takes a long time to analyze the data. You can see that most of the galaxies are within 300 megaparsec. So 200 probably is the peak.
We have a comment that came in through the chat. Well, I'll let you pick that up because it's the questioner wants to send the article where the methods of analysis are given and described. And so we know of some galaxies that have multiple nuclei, but are those too widely spaced to actually produce any gravitational radiation at this point?
Right. So the ones we can resolve pretty much, they are at kiloparsec. Most of the ones that we have seen as dual AGN, where they have two active supermassive black holes, they are at kiloparsec scale. We have one let's say, the record holding binary was resolved with very long baseline interferometry. That's at 7 parsec separation. The ones that emit gravitational waves that can be detectable, they have to be at milliparsec separation. So in that scale, it's almost impossible to resolve the two black holes.
I'm sorry, what distance apart did you say they have to be?
A milliparsec.
Oh, a milliparsec. Okay,
Yeah.
thank you. 1,000.
So the resolution, if we think that these are, let's say, beyond the local universe, the resolution is micro arc seconds. So
okay.
even the Event Horizon Telescope maybe doesn't have this kind of resolution.
Right, right. We do have a question about how does the constraint depend on unknown gas dynamics?
So for this here, for these constraints, we don't make any assumptions. We just have the constraints from the gravitational wave, and we just convert the strain upper limit to a chirp mass upper limit and the mass ratio upper limit. So for this, it's just observational data. So we don't make any assumptions. If we think more about the background and the population of binaries, then for sure we will be affected by how the binary evolves.
Okay. Are there any other questions? Let's give a minute here for people to send in any other questions if they have them. Yes. Are your low Z galaxies based on the WISE survey?
So these were based on the 2MASS catalog. So 2 micron, I don't remember the acronym. So we haven't used WISE yet. WISE can probe deeper. So that may be the next step in building a, like, let's say, a multi-messenger catalog that covers the entire sky and goes to higher redshift.
Now, you've mentioned that these results are based on the 11-year data set, and they're now up to 14 or 15 years. Does the sensitivity go approximately linearly with the length of the data set?
I think it's the square root of the baseline. Yeah.
Okay,
but
so
it helps that it's not only the baseline that is improving as we go to the newest data set. We have more pulsars, and that also really helps with the sensitivity.
Yes. Okay. Oh, finally, we have time for one more question, and here is one. Is there potential LIGO observatory that could match the observable NanoGrav frequencies?
No. So the thing is, the gravitational wave has a wavelength. And the wavelength of this, the nanohertz frequency gravitational waves, it's bigger than the Earth. So you cannot think that we could build an observatory on Earth that uses interferometers and can probe supermassive black holes. Of course, LISA is sort of the idea behind LISA, that is, you build a gigantic interferometer in space that will detect millihertz observatory. So not quite the nanohertz that we can probe with Pulsar Timing Array. Remember, here we have a galactic scale detector. But let's say the 10 to the 5, 10 to the 8, maybe 10 to the 7 supermassive black hole binary will be detectable with LISA, which is an interferometer in space that has millions of kilometers of interferometer arms.
Thank you. We have a question about the specific current constraints on M87.
Let's go to M87. So M87 is here, the bottom bar. So I think here we can exclude for sure a major merger. So that is 1/4 for the mass ratio. I'm not sure if I have M87 in one of these. But for sure, we have it in the paper. There is a table with the different galaxies we can probe. M87 is one of those. And we have the limits in all the different frequencies that we probe.
We have time for one more final question, and it's a very provocative one. Any updated estimate on when we could expect to detect the stochastic background?
Well, so the last data set we analyzed for the stochastic background was the 12.5-year data set. And in that one, we see a common red noise process across many pulsars. We don't see the spatial correlations that we need to claim the detection of the gravitational wave background. Now, there has been some theoretical work that uses the amplitude that we can infer from the 12.5-year data set. So that is a paper led by Han Paul. And if what we are detecting is the first hints of the background, there is an amplitude we can infer. And if that is the gravitational wave amplitude, the spatial correlations should be detectable in the 15-year data set. So the one we are currently analyzing. It could be something else, but I think the data will show us.
Well, that's all the time we have for today, and I'd like to thank you very much for a fascinating talk. Let me point out that in this series, in the coming months, we will have a talk on exactly the stochastic gravitational wave background and its effect. To remind everyone that this presentation will be able to be viewed on our website, and please return with us 2 weeks from today, March 2nd, for Green Bank's own Jim Jackson talking about RAMPS, the Radio Ammonia Mid-Plane Survey. Thanks for joining us today, and we look forward to seeing you then.